Okay, students, welcome back. In the last session, we have discussed about calcination and roasting. So, which are the two types of isolation of metal, crude metal from the concentrated ore. So, in that second step was reduction of the metal oxide to metal. Now here in the last part I have told you that some metal oxides may be reduced very quickly and in a very easy manner, but in some cases it may be difficult for us to reduce some of the metal oxides. Now in such cases we need to apply some thermodynamic principles which we have studied in first PUC. Now here I have explaining about this thermodynamic principles. So in the first PUC we have studied about this equation, that is delta G is equal to delta H minus T delta S. Here delta G is Gibbs energy or Gibbs free energy, delta H or the change in Gibbs free energy, delta H is change in enthalpy, here T is the temperature, delta S is the change in entropy or randomness. Now when the reaction is feasible or when the reaction is possible, that is it will occur by itself, if the delta G of any reaction, if it is negative, if this is negative, then reaction will occur. If this is positive, the reaction will not occur. Okay. So in order to have delta G negative, what we should have? So in order to have delta G negative, we should have this should be negative. Delta H minus T delta S should be negative. Right. Now in some cases this delta H it will be negative only, and the product of temperature and delta S, in the most of the cases delta S is positive. This is positive. This term should be negative in order to be a reaction is possible. Now I will take one example, that is iron oxide undergoes iron plus half O2, that is reduction. Now here the delta G value is positive for this. The delta G for this reaction is positive. Now this reaction is not at all possible because we have delta G is positive. I will take one more reaction, that is C plus half O2 gives CO. Now the delta G of this is negative. Let us consider this may be plus 40 and this may be minus 100. So these are all not real values, real figures, these are all fictitious figures I have taken here. Now this reaction will not occur as this has delta G positive, and this will occur because we have delta G is negative. Now if you combine these two reactions or couple these two reactions, what you will get? FeO plus C, which gives Fe plus CO. Now when you couple these two reactions, the delta G should also be added. Now you will get what? Minus 60. So now this reaction is possible. This reaction is possible because we have delta G is negative here. Delta G is negative. So standalone this reaction 1 is not possible. Reaction 2 is possible. If you combine these two reactions, then the whole reaction is possible. Now by taking the advantage of this principle, we will reduce this iron oxide using this carbon as a reducing agent. So this is called reducing agent. This is nothing but reducing agent. Okay, so this is one example how we consider, how we apply thermodynamics in the metallurgy, or how we apply thermodynamic principles of in metallurgy. Okay, now we cannot have these calculations all the time. So for that we have one diagram called Ellingham diagram. We have one diagram called Ellingham diagram that is given by H.J.T. Ellingham. And this diagram is nothing but, it is a plot of temperature versus delta G, or change in Gibbs free energy for 1 mole of oxygen consumed for oxidation. So in other words, you can say for oxidation reaction, we have this H.J.T. Ellingham has given one plot of temperature versus delta G value. Now using this diagram or this plot, you can guess which reducing agent can be used for a metal oxide, or the conversion of metal oxide to metal, or to reduce any metal oxides to metals. Okay, now here these are all the delta G values, minus 1100, 1900, like this. Then you will get 0 at the end. Now temperature here 0 degree Celsius or 273 Kelvin, it will go up to 2273 Kelvin or 2000 degree Celsius. Now I will consider the same example of iron here. So we have iron here. So as I told you, this is not the reaction of reduction, it is a oxidation. All the metals are oxidizing here. Okay, here copper is oxidized, iron is oxidized, or aluminum is oxidized. Okay, in every case it is oxidized. So what we need this metal from this oxide, FeO. So we need reverse of this reaction, not this reaction. Okay, but the values are given for this reaction. Now for this Fe plus O2, for the oxidation of this iron into iron oxide, the delta G value is around minus 450. It is around minus 450. Okay, I'll write here minus 450. But what we need the reduction of this. We need reduction of iron oxide. Then what we have to do? So this will become plus 450. So delta G value for that will become minus 450 at 0 degree Celsius. At 0 degree Celsius or 273 Kelvin. So I'll consider at T is equal to 0, the temperature 0, the delta G value for the reduction of this iron oxide, that is plus 450. If you look into this graph, you will see minus 450, but that is given for the oxidation of this metal. Okay, so for reduction, when you are reversing this equation, the minus value becomes positive. Now this is plus 450. Okay, at temperature T is equal to 0. Now I will combine this reaction, this one. I'll combine this reaction, that is carbon plus oxygen gives carbon dioxide. Okay, what happens? So the delta G value at 0 degree Celsius, that is minus 350. But here we are considering this direct reaction only, no reverse. So this will minus 350. what is answer? You will get plus 100 only. So still the delta G value is in positive. So if you combine this and this reaction at 0 degree Celsius or at 273 Kelvin, these two reactions, this one and this one at 0 degree Celsius, still the delta G value is positive. That means this reaction, even though if you couple these two reactions at 0 degree Celsius, it is not possible. It will not feasible, or this reaction will not occur, or the reduction of this iron oxide will not be possible at 0 degree Celsius using this as reducing agent. Now, if you increase the temperature, at this, maybe at this point, so it is around, so I will take at 800 at temperature 800 degree Celsius, the delta G value for this reaction is somewhat around minus 300. That means the reduction value, so for this it is given minus 300, but for reduction it will become positive, so that is plus 300. And for this one, for the oxidation of carbon, it is still lies 350, that is delta G is minus 350. Okay, so you will get minus 50, that is delta G value is minus 50. So now if you look into this delta G value, this is negative. So if you couple these two reactions at 800 degree Celsius or 1073 Kelvin, this reaction will be feasible. The reduction of this iron oxide using this carbon as reducing agent is possible at this temperature, but at 0 degree Celsius it is not possible because the delta G value is positive. So by looking at this graph or this plot, you can decide that the curve which is lies below to the any of metal oxides can reduce the metal oxides present above in this graph. So for example, this magnesium metal can reduce aluminum oxide up to this temperature, up to 1200 degree Celsius. So after this temperature, the aluminum can reduce magnesium oxide. So this graph is useful for predicting which is the reducing agent and at what temperature we have to carry the reactions. So by looking at this graph, we can decide at what temperature we have to perform the reaction, which reducing agent will be the suitable one for reduction of any metal oxide. So now the below one, the metal which is lying in the below at the end of this graph, so that is magnesium. Now this magnesium can reduce any of the oxides present above it. So that means this magnesium can reduce zinc oxide, it can reduce iron oxide, it can reduce copper oxide, any of the oxides of metal. And this zinc oxide, so it cannot reduce aluminum oxide, or the zinc metal cannot reduce aluminum oxide, it cannot reduce magnesium oxide because it present the line or the line of this zinc is present above than this. Okay, so this is just a simple idea that whichever the metal is present below can reduce the oxides present above it. Okay, so this is the use of this Ellingham diagram. In this Ellingham diagram, so you can observe in all the lines are straight, but at some point there is a sharp change in the values, that is the lines are changing in this point or in this point, like here. So this sharp change in the values of this delta G or the change in Gibbs energy is nothing but it is an indication of change in phase, that is it may change of state, physical state, like solid to liquid or liquid to gaseous, like that. So this point actually the reactants are converting into if it is in solid state, then they are converting into liquid or into gaseous phase. So we will be discussing about the applications of this Ellingham diagram in detail, in particular to iron oxide and some other oxides in later classes. Now I hope that you understood this Ellingham diagram. Now, and this Ellingham diagram is not the perfect one, so it has some limitations also. So there are two limitations of this Ellingham diagram, so that is I have written here. The graph or the Ellingham diagram doesn't explain about the kinetics of the reaction. It doesn't explain about the kinetics of the reaction. What is meant by kinetics? So kinetics of the reaction is nothing but how fast the reaction takes place, or the rate of reaction. Rate of reaction. It doesn't explain about rate of the reaction. Okay. So one more limitation here is that the interpretation of this delta G value or the this value, the Gibbs energy value, change in Gibbs energy value is based on K. What is K? It is equilibrium constant. So we know that delta G naught or the standard Gibbs energy, Gibbs free energy change is equals to minus RT ln K. So this K is nothing but equilibrium constant. So by this delta G value is purely based on the K value or the equilibrium constant value. So equilibrium constant. So this equilibrium constant, when this K will comes into picture, it comes into picture only when the reaction is in equilibrium. So this graph pre-assumed that all the reactions taking place are at equilibrium only. Thus it pre-assumed that the reactants and products are in equilibrium. So the reaction must be in equilibrium. So sometimes in these reactions, the metals or the metal oxides, the reaction may not be in equilibrium. In some cases, like if the reactants are in solid phase, then this is one of the limitation of Ellingham diagram.